AP Calculus, section 4.1, page 5. All right, we are starting here. Let's analytically find the absolute extrema of f of x equals secant x for x between negative pi over 3 and 4 pi over 3. Then we'll verify your answer graphically. All right, finding the derivative. F prime of x is, all right, the derivative of secant is secant x tangent x. Now we are interested in where that derivative is equal to 0 in undefined. When you've got secants and tangents or cosecants and cotangents, flip them to sines and cosines. And we'll have sine x over cosine squared x. When we do that, we can definitely see the difference in the numerator and the denominator, and it's easier to find out where the derivative is equal to 0 and where it's undefined. F prime of x equal to 0, f prime undefined does not exist. None for now. That piecewise defined function will come up shortly. Looking where the derivative is equal to 0, where the numerator is equal to 0, so where sine is equal to 0. Think back, unit circle. Where is sine equal to 0? Sine is equal to 0 at 0, pi, 2 pi, 3 pi, etc. X equals 0, pi, 2 pi. Or x equals some k times pi. All right, now in this interval, which of these show up? For x between negative pi over 3 and positive 4 pi over 3, I think we're going to see x equals 0 and just pi in that interval. So there's the only critical numbers in that interval. All right, now let's find where f prime of x is undefined. That's going to be where the denominator is equal to 0, where cosine is equal to 0. Cosine is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, etc. Negatives of those as well. In this interval, which ones? From negative pi over 3 up to 4 pi over 3. Visually, negative pi over 3 is here, up to 4 pi over 3 here. Okay, so the critical numbers here are going to be at x equals pi over 2. That's that one. And, oh, I think that's it. Just pi over 2. Yeah. So that also is a critical number in the given interval, just those. All right, so once we have those critical numbers, then we'll set up our t-chart. And let's check the endpoints. Endpoints are negative pi over 3, 4 pi over 3, and then our only critical numbers, 0, pi, and pi over 2. I'm going ahead and looking at those. So we need to substitute these x values, back into the original equation. So we'll need the secant of negative pi over 3. Negative pi over 3, secant there is 1 over cosine. Cosine's half, so 2. 4 pi over 3. Secant here is going to be negative 2. At 0, plugging that in, the secant of 0. 0 is right here, that's going to be 1. At pi, negative 1, pi over 2. Oh boy. Secant of pi over 2, that's undefined. Okay, now we have a little bit of an issue here. That came out to be a critical number. How could it give us something that's undefined? Because it's not really a critical number. This pi over 2 is not really a critical number because even though it showed up here, it's not in the domain. It's non-existent in the original function. So that's not really a critical number. Because that number, it is not defined in the original function. Not defined in the original function. Okay, so that one's out. All right, now that leaves us these guys right here. So looking at this list, it looks like we're going to have an absolute maximum right here. And it looks like we have an absolute minimum right here. All right, now let's verify this answer graphically. Oh, let's use a calculator for this one. Let's do secant. It's 1 divided by cosine. Make sure you're in radians. You are. Zoom. We'll go zoom 6. Yikes! Holy mackerel. Let's drop this down a little bit here. Window. Negative pi over 3 to 4 pi over 3. Let's go a little bit bigger. About negative pi over 2 to, I don't know, what do I say, 2 pi? And let's count off by pi over 2. I'm going to count off by pi over 2 or pi over 3s. Oh, let's go pi over 3s. And y's, let's go negative 5 to 5. Yeah. All right, so where are we graphing this thing? What are we interested in? From negative pi over 3. And remember, we're counting off by pi over 3s. So it's starting right here at negative pi over 3, right there. And going up until 4 pi over 3. 1, 2, 3, 4 pi over 3 right here. So when we're looking at this graph, when we copy this onto paper, we're going to have an asymptote. Let's see, negative pi over 3 is going to hit here, comes down there. We have first asymptote right here. And this comes back up that way. And then we have another asymptote, 1, 2, 3, 4, a little bit past the fourth, 1, 2, 3, 4. So it's out here. And we're seeing that. Okay, so now let's talk. This said at negative pi over 3, the 2 was an absolute maximum. That point right there is negative pi over 3 comma 2 as an absolute maximum. Absolute maximum. Is that an absolute max? No, it's not. It's a relative, but it's not an absolute because this piece keeps going up over here. Likewise, this one said at 4 pi over 3, right down here, we were going to have an absolute minimum. That is not the absolute minimum value. These answers are wrong. Actually, we have a relative minimum right there. That relative minimum is 1, and it occurs at x equals 0. And we have a relative max at negative 1, of negative 1 at x equals pi. Here's the answer. So what happened here? What happened was that this didn't really fit the extreme value theorem because the function is discontinuous on the given interval. This didn't hit, it doesn't fit the extreme value theorem because the function is discontinuous. Doesn't satisfy the initial conditions, INITIAL, conditions of the extreme value theorem because the function is discontinuous on the given interval. So, what you think are absolute extremas might not be, because not guaranteed, because the extreme value theorem doesn't hold true. Okay, so another tricky one there. All right, how about this one? I want you to find the derivative at each critical number and determine the local extreme values of y is x to the 2/3 times x squared minus 4. Use a graph to help determine the information. All right, so here we go. Find the derivative at each critical number. So I better find those critical numbers first. Let's find the derivative. Oh boy, we got a product rule going on here. So first, x to the 2/3 times the derivative of the second, which is 2x, plus the second, x squared minus 4, times the derivative of the first, 2/3 times an x to the negative 5/3. Let's clean this up a bit. This is going to be 2x to the 5/3 because I added the exponents here with this x to the first and that x to the 2/3. Plus, let me distribute this 2/3 x to the negative 5/3 through the parentheses. And that's going to give us 2/3 x. All right, that's 6/3 and negative 5/3. Uh-oh. Well, gosh, it would be nice if I could subtract. And some of you all are having a heart attack. I know you are. I'm so sorry. 2/3 minus 1 is not negative 5/3. It's negative 1/3. Better? Sorry. And sometimes I make a mistake and I'm going along and it just doesn't click, so then I look back and figure out where my mistake was. So let's go again. So 2/3 x to the negative 1/3, distribute that through, that's 6/3, and a negative 1/3, that's 5/3, and a 2/3 x to the negative 1/3 times this 4 is minus 8/3 x to the negative 1/3. All right, these two right here are like terms, so we can add those. 2 and 2/3, that's 8/3 x to the 5/3 minus 8/3 x to the negative 1/3. Let's go ahead and factor. We can pull out an 8/3 x to the negative 1/3. From this first one, we need an x squared, because negative 1/3 plus 2 is 5/3. And from the last one, minus a 1. Oh, look at that. That factors. Let's clean this up. Pull this x to the negative 1/3 to the bottom and factor this x squared minus 1. We'll have an 8 times an x plus 1 times an x minus 1 all over 3x to the 1/3. All right, now still need to find the critical numbers. That was just the derivative. So let's set y prime equal to 0, y prime undefined, y prime does not exist, none of these, y prime undefined where the denominator could be 0, That's at x equals 0, where the numerator could equal 0, at plus or minus 1. Here's your critical numbers, these three. Okay, now the wording was a little bit different on this one, so let's be careful. Find the derivative at each critical number and determine the local extreme values of that function. So, we have x, y, and y prime. Alright, so our critical numbers are 0, 1, negative 1. Those are the critical numbers. I didn't ask you about endpoints and extreme values. That's all you can do. The y values here. So let's plug these back into the original function. Plug a 0 in. That's going to give us 0. Plug a 1 in. 1 to the 2/3. That's 1. And there's negative 3. Negative 1 to the 2/3. That's negative 1 squared, which is 1. And then the cube root is 1 times still negative 3, so that's negative 3. Alright, now find the derivative at each critical number. The derivative at 0 was undefined. The derivative at x is 1, that derivative is 0. The derivative at x is negative 1 is 0. Alright, that's all we can get right now. Now use a graph to help determine the information. Because we don't have a closed interval and there's nothing going on like where we could use the infinities or anything like up here where the function was discontinuous. The only thing we can do at this point in your calculus career is go to a graph. So let's graph this, x to the 2/3 times x squared minus 4. And there we go. So, if we sketch this, this is what we see. And right here at negative 1, we have a horizontal tangent. At negative 1, horizontal tangent, the y value is negative 3. At 1, horizontal tangent, the y value is negative 3. At x is 0, we hit this point 0, 0, and the derivative is undefined. It's almost vertical here. Almost vertical. We have a cusp. We have a cusp going on. Alright, now go back. Find the derivative at each critical number. Done. And determine the local extreme values. Local extreme values. There is a relative minimum equal to negative 3 at x equals negative 1. Actually at both, plus or minus 1. There is a relative max equal to 0 at x equals 0. And we are done. Lots of crazy stuff going on here. Take your time, think about what you're doing.